Alrighty, so looks like we're about three after, so I'll go ahead and begin. Good morning, everyone. Thank you for joining Dr. Margulieux's session. I'm going to read a quick bio. Actually, before I start the bio, if you could please fill out the attendance form that we have for every session. It is pinned up at the top of the chat. While you're doing that, I will read her bio. So Dr. Lauren Margulieux is an assistant professor of learning sciences at Georgia State University. She received her PhD from Georgia Tech in engineering psychology, the study of how humans interact with technology. Her research interests are in educational technology and online learning, particularly for computing education. She is coordinating an initiative in Georgia State's teacher preparation programs to integrate computing into pre-service teacher training in all disciplines to broaden participation in computing and provide additional teaching strategies. She also directs the computer science endorsement to certify teachers to offer standalone computing courses. Without further ado, Dr. Margulieux.
Thank you so much, Terry.
You're welcome.
So I don't want to spend too much time saying why I think this work is really important. I assume if you're here that you're somewhat interested in it already, but I did want to expand a little bit and say that my job basically is working with the teacher preparation programs at Georgia State. I'm in the College of Education as well. And so I spend most of my time working with teachers, with the faculty in those programs to say, what is it that your teachers find difficult to teach? Or what do you want to add some technology to something to maybe make it a little bit more interactive, something like that, but you don't know how. And so those are the conversations that I have with our faculty and where all of these activities came from. And so we focus on integrating computing into required courses so that it's truly reaching all students. And that's important to us because in Georgia, computer science isn't a requirement. So really the only way to get people interested and have any sort of exposure to computing, or to ensure that they have exposure to computing, is to integrate it into existing courses. So that's the sort of motivation behind this work and where it came from. Today, I'm hoping to get through 3 activities, one in science, one in English, and one in math. And the math one's probably going to be pretty short. It's very open-ended, so that's okay. Like I was telling Terry before, I think a lot of you were in here, it's more important to me that we're going at a pace that people can follow along than that we get through everything, so to speak. So there'll be lots of pauses, especially in the first activity, to make sure that, we're all on the same page. So if you want to follow along you can see my screen. On the right-hand side of the screen is sort of an activity guide that I've made for the first activity we're going to do. And then on the left-hand side of the screen is the programming environment that we're going to use. Oh, Terry already shared the link. So that link is to the right-hand side of the screen, the activity guide. And so this first activity that we're going to do is for middle school science. It can be sort of tuned down to elementary or tuned up to high school, but it's geared at middle school. And what we're going to do is make a program that draws electromagnetic waves. So visualization tools are very common in science. At least this is what the science education faculty told me, because obviously you can't see electromagnetic waves. So having some sort of visualization is a good way of teaching these concepts. And what having the computer program allows us to do is it allows us to be very flexible and very dynamic in how we make this visualization. So instead of drawing a wave that then is static or some other sort of thing, this allows students to play around with it a little bit and get familiar with the concepts. So I'm going to start just from opening pencil code. We like to use pencil code because it's a block-based environment that can switch to text-based if students are sort of getting the hang of it, and if they want a little bit more can even upgrade into JavaScript. So if they are on that path towards a more authentic programming language, and if they want more of a challenge, they can experience that through pencil code as well. I'm just going to log in and create a new program. And I'll call it Constellations. So the thing I like about this activity is that so you can either follow along or just watch, whichever one you want to do. So the thing I like about this activity is that you show people the picture on the lesson plan, and you say, we're going to make a visualization that looks like this using a program. And they say, I don't know how to do that. I don't even know where I'd start. And I'd say, great. That is where you start with computer science. You don't have any idea how you're going to get to the end, but we're going to take it step by step, and eventually we'll get there. So I really like this activity for adding different features along the way that sort of upgrades things as they go and allows you to build upon skills. And so that's how this lesson plan or the activity plan is sort of parsed out. So you have part A, we're just going to make an algorithm, which is going to be drawing a wave in pencil code. And so step one here, if you can't read, not that you can't read, but if you can't like see it, is logging into pencil code, creating a new file. If students don't have any experience with it, sometimes I'll have them do an activity where they sort of draw out their name. And so I'll give them like a little 2-3 minute tutorial that's just how pencil code works, is that you drag these blocks from the left-hand side into this workspace, and then you hit run. So you can see the turtle did, it moved forward, and then it turned to the right, which is what forward, or FD and RT stand for. Pencil code is free. And then there's different pieces. So you can move the turtle, you can draw. So if I add a pen, I can change it to whatever color I want and how many pixels across it is. And then you restart, and now it'll draw as you move. For what age group? We use it elementary through middle school, sometimes into early high school. And so you can just show them how the art and the move are the main ones that we start with, because those are sort of the easiest, and then we'll have them draw their name, which is a common sort of activity for this sort of programming environment. And that helps them get a little bit familiar with it. And then we sort of clear it out, so you can either drag each of these blocks individually, or you can select all of them and drag them out of the working space to delete them. And now we get started with actually making the wave. So we want to start with a pen. We'll say purple's good. And then we just want to draw a wave. Don't think at all about how it's going to make multiple waves. Don't think about how it's going to use variables. We're just going to draw a wave for now. So we want it to go forward. We want it to turn right, go forward, turn right, forward, left, forward, left, forward. And then we'll run it and see how it works. And this part is really important, is the running it and seeing how it works. And I'll often make intentional mistakes. So you could say that the baseline for the wave is in the middle there, but really how we want it, or how you would draw it in science, is with an additional forward. so that you're starting at the baseline and going above and below it. So I'll add an extra forward there. At this point, I'll also say that you can add a speed to make it go faster. And so speed of 10 is a little bit faster, or a lot faster apparently. So this is the first step, is we just made an algorithm that the computer is going to follow. And now we have a base wave. So that's a good starting point. Now what we can do is we can add new things. So in this case, the first thing we're going to add is a loop so that it'll draw the wave multiple times. So we go into the control menu and we will grab a for loop. The for loop will let us say how many times we want it to repeat. And then we can select all of these by dragging and selecting and put them in the loop. And so now it's going to draw it 3 times. It's going to go off screen, which is fine. And so now we have a loop, but it's a little wonky, right? So there were unintentional consequences of the loop, which is that now it's going off screen. So something that we can do is we can move the start point to the left. So you can add a move to. And so how you select multiple blocks is just click off of one of the blocks and drag across multiple ones. Or at least that's how I do it. I'm not sure if there's multiple ways. So if we want to do a move to, where, I'm pointing to my screen like y'all can see because I still, anyway. So where the computer, or where the little turtle starts is, it's an XY plane. There we go, XY plane, and it starts in the middle at 0, 0. So if you go to the left, it's going to be negative numbers. If you go up, or negative X numbers. If you go to the right, it's going to be positive X numbers. If you go up Y, it's going to be positive Y. And if you go down, it's going to be negative Y. And it's measured in pixels. And so if you, like everyone else, don't know exactly how many pixels your screen is, this can take a little bit of guesstimation work. So say we're going to go to negative 100x and 0. And this is the part where you can just play with it and see what happens and what sort of mistakes and unintended consequences you get. So this one, I added it after I put the pen down. So we want to move that above to where the pen, so there's no pen when it first moves. And we see that it doesn't quite go as far to the left as we want it. So we'll just try doubling that. And now you can mostly see all of the wave as it loops multiple times. And the thing I really like about when I'm teaching this is showing the mistakes and showing how you sort of recover from them, is that you're showing it's no big deal, as you know, computer programmers often do, is, you know, you add something, you forget that it's gonna make this consequence down the line, and so you just fix it. So it doesn't have to be perfect the first time. You just have to think through how you're going to fix each thing. All right, so if we wanted to shorten this wave so that we could see the entire thing, you can sort of trace through the code and say, okay, the first forward is 100, and then the second forward is 100. So I'm going to change that to 50 so that it's shorter. And then we go down twice, and then we go to the left. I'm going to change this again. So now we have it shorter, so we can actually see it. But it's really inconvenient every time we want to change something like that to have to change it, to sort of like trace through the code, see where we need to change it, and then change the variable or change the number of pixels that it moves. So what we want to do is we want to add variables so that we can just change that value in one place and it will apply to the entire code. So that's the next part of the activity. I should ask, do we have any questions at this point before we start adding variables?
We have a question from Ryan. How do you?
So that's a good question. You can't add comments in the text-based side of pencil code. Now's a good time as any that you can go to. So if you click this button, there's a little outcrop here. And if you mouse over, it says click for text. So if you click that, it'll change to the text-based side. And as long as you add something that it recognizes in the text-based side, you can switch back to blocks and it'll turn it into a block, even if that block is not on the menu. So for example, we could add here a comment that says, this is now drawing the wave. And it'll add that as a comment. So for Ari's question about whether students should already understand what a for block is prior to this lesson. So if it depends on the class, you absolutely don't need to know what a for loop is, what a variable is, what a conditional is before you start this. It just depends how long you're going to spend on each of those concepts. So this is an example to demonstrate the concepts, but if students didn't know beforehand what a for loop was, what a variable was, you'd want to stop at that point and do a little bit more instruction about what those are. If they do know what those concepts are, then they can apply them to this case. So this activity can take anywhere from, I'd say the minimum's probably an hour and a half, but it could take, much longer. What I like about it is that you're simultaneous, like you're really just using the program in a science class, if you were doing it in a science class, to reinforce the concept of waves. So when we start adding variables, we're going to start talking about wavelengths. We're going to start talking about amplitude. So it's good ways to talk about those activities. And then if you were doing this in a computer science class and you just wanted to do a science integration to sort of connect back to something that students had already learned in their science class as building upon prior knowledge, then you would focus more on the computing concepts. So Alana's question, I would say give it at least 90 minutes more if they haven't experienced any programming before. For Laura's question, any of the links that we add along the way, you can access at any time. So I've sort of set them up as activity guides. They're not full-blown lesson plans, but they're sort of activity guides that go step by step. And you can use them whenever you want. All right, moving on to variables. So yeah, in the text, it's probably too small for you to read, but we do start talking about, this is a good place to start adding comments. It starts getting a little bit complicated. So we want to add a variable, which is in the operators menu, that is wavelength. What I found when working with students is that the top bug in this program is misspelling wavelength. So just keep in mind. And we want to add amplitude. So the wavelength is how wide the wave is, for those of you who, like me, had not thought about this for at least 15 years. I had my science educator friends reteaching me all the things about waves. But the wavelength is how wide it is, and the amplitude is how tall the wave is. So instead of moving up 100 pixels, we want to say we're going to move up for the amplitude. Still turn right 90 degrees. I know it's not, a perfect wave, but as a scientific model, everything's an approximation anyway. So that's a good place to talk about scientific models if you're using this in a science class. We want to move forward the wavelength. And this is a good opportunity to talk about wavelength, because a wavelength is for an entire cycle of the wave. So the wavelength in this case is only going to be half of the wavelength. And so if you type wavelength and then /2, it'll convert itself into this. You can also add math operators from the operators menu. So if I took that out, I could add this division operator and type in wavelength and 2. And then to clean up the code a little bit, I'm going to get rid of this forward and say amplitude times 2, because the amplitude is from the baseline up or down. Again, wavelength divided by 2, and then amplitude here. So these variables say 0 right now. So if we run this, it's not going to move anywhere. But if we add, the wavelength is 50 is what we had it before, and the amplitude is 100, which is what we had before. Or actually, the wavelength was 100 before because it was 50 for each. It's no problem, you can just run it again. So now it looks the same as before. And now you can, if you're in a science class, you can do an activity that's sort of a prediction activity. That's, okay, what happens if I change the wavelength to something smaller? Is it going to get narrower? Is it going to get wider? You can change, what if I change the amplitude to smaller or higher? You can have them draw, in a low-tech space, what it's going to look like. You can try to get the proportions correct based on what percentage of the current wavelength. So if I change the wavelength to half, then it should be half as long. If I change the amplitude to twice as tall, it should be twice as tall. And so you can reinforce concepts that way at this point. And so that's the value of adding the variables to this program, is that you can change these values in one place, and then the visualization will dynamically change with it. Any questions at this point? And then we can also add comments. Something else that we added at this point, because the students, when we went into a classroom and working with students, they're like, well, you always want to have a resting line or the baseline in a wave. So something that we added later was adding this baseline, where after we moved it to x negative 200, y 0, move the purple pen down here so it doesn't apply until we're drawing the wave. But we can add you can either select from the menu or you can just type a color. We did a black, and then we turned it to the right and moved forward for the length of the screen. And then you can either turn it back to the left and retrace, or you can just add another move to get back. And so when we first did this, this is what happened, because we forgot to turn the turtle back right side up, because we always think, you know, starting with the turtle facing upward. But again, it's no problem to have it just restart. So we also added a resting line. All right. And then if we want to, this is all one wavelength. So if you're thinking of electromagnetic waves as representing colors on the color spectrum, if it were all one wavelength, it should all be the same color. But in the image that we showed at the front, it was the wavelengths were getting shorter and shorter, and therefore the colors were changing from purple, blue, green, yellow to red. Or do I have that backwards? What's the longest wavelength? Red's the longest wavelength, all right? Yeah, I had that backwards. So you start with the longest wavelength, red. You could also do it the opposite, but we started with the longest wavelength being red. And again, we want to have the computer do this automatically. So we drag out the base of our loop. You can do this with a for loop, but I like using it as an opportunity to introduce the while loop. I think it works better with a while loop, and it gives you the opportunity to talk about the difference between for and while loops. And the reason that it needs to, or it's better as a while loop, is going to become apparent in just a little bit. So we're going to change it to, actually, let's do it as a for loop for now, because this is, I'm walking you sort of through the process of how I discovered what this needs to be, so that, you know, you can see what a common thought process would be. So we have our wave, and then at the end, we want to update the variable of wavelength so that it gets shorter. So we're going to add a variable that's wavelength, same as before. And we're going to decrease it by 3. We'll start with a wavelength of 50. So if you do a for loop that is more than 3, let's say it's 25. If you do a for loop and you decrease the value by 3 every time, eventually the value is going to get to 0, and it's going to start going backwards. So this is the point at which I discovered that a while loop would be better here. So you can see it started going backwards. And so again, it's not only an opportunity to talk about the difference between for and while loops, but I think it's a better functionality here. So we'll drag this out, replace the for loop with a while loop. And we'll say while wavelength, that is the wrong operator. while wavelength is greater than 0 or greater than 1, either one, it will continue to decrease the wavelength. I'm also at this point going to change the width of the pen to less than 10 pixels because it gets very murky. So if we run it again, the wavelength is slowly decreasing. And when it gets to a small enough number, it'll just stop. All right, any questions at this point? All right, so that's how we get our wavelength to decrease, is adding at the end of the loop the variable to change to the current value of the variable -3, and we change it to a wavelength so that it doesn't start going backwards. You can do it with a for loop and have them calculate how many times it should repeat, but then you have to do it every time you want to change the wavelength. So that's why I like a while loop better here. Now we have to add the colors, and the colors is the last part. And the way that we add the colors is we want to say, and we started to like sketch out this having the actual colors specified in the program connected through some mathematical operation to the value of a wavelength that would be red or the value of a wavelength that would be orange. It was quite a lot. So we just ended up doing arbitrary values for red, orange, yellow, and blue, but you could do it as an operator if you wanted to make it even more aligned with the actual values of an electromagnetic wave. So what we added was some conditional statements. And it's going to be a series of if-elses. And you can add, this one's a little bit tricky in pencil code, but you can add additional else's by clicking this little plus button here. And so now we're going to go into the art, and we're just going to set the color of the pen to depend on the wavelength. So this is not the right operator. So if wavelength, let's see if I spell each of these wavelengths right, because I guarantee you I don't. If it's 40, we're starting at 50, so the first few will be red. We'll call them red. And then, so if the wavelength is greater than 40, it'll be red. The else if then says if that's not true, then if the wavelength is greater than 35, it'll be orange. And then at this point, or maybe a couple more into it, the students or you as the teacher might say, you know, it's really tedious to be dragging these blocks. So this is the last step of the activity. So I think it's a good place, if you're comfortable and if your students are comfortable, switching to the text-based side to get familiar with the text-based approach. And when you're working in the text-based side, especially at this early stage, if you haven't been working with text-based languages before, just use the previous line as, you know, the template, and you're just going to change the values. So we can even copy and paste. Greater than 30, then pen is yellow. I'm going to copy and paste that line. Change this to 25. Change this to green. If you hit enter from the end of this pen green 2 line, it will still be within the if else, so you have to hit backspace to go back, if that makes sense. And then this last part, the last else, it doesn't follow the same template as before. So we'll usually go back to the block spaced at this side. So you can see it all switched back to block spaced as long as we write something that the computer recognizes in the text-based side. And then the last one is going to be purple. Actually, no, that's not. So you can trace through this with your students, saying if the wavelength is greater than 40, the pen will be red. If that's not true, then if it's greater than 35, it'll be orange. If neither of those are true, then if it's greater than 30, it'll be yellow, and so on until you get at the end, which is if none of the above is true, then it'll be purple. And we hit run and see how it goes. And it works. It probably won't work the very first time that you work through it. I know it didn't work for me, but that's the last step to get to the image that we had at the beginning. Although it looks like the image that we have at the beginning also prints the frequency, which was part of a different thing. But that's the whole activity. Like, you know, we went through it in 35 minutes or so. That's way faster than we go through it in an actual classroom. But I wanted to show you all a couple of other activities as well. So I hope that made sense. Any questions about this activity, pencil code? Yes, so you can switch it to text, which I believe they call this CoffeeScript instead of JavaScript, because they're cheeky like that. But if you go to languages up here in the corner, you can, oh yeah, you can switch it from CoffeeScript to JavaScript. And it's all broken. I'm not sure why that's all broken. Well, yeah, you can't switch to blocks in JavaScript. It should convert it. I would have to look into why that's not working. Oh, it might have to do with the comments. Oh, it only works if you switch it to JavaScript before you do the blocks. Well, lesson learned. Any other questions? All right. So now I want to go on to the English activity because I think, you know, it's a little bit easier. It maps a little bit easier to do computing activities in science or math, but it's just as valid to do computing activities in English or humanities. You often just, there's not as many examples, so you have to be a little bit more creative with them. For Alada's question, I don't know that I've seen a teacher account for students. You can share in a number of ways. So you can, if you click on see it here, it'll just show the output. If you click share code, it'll share everything that you have in the program. For Melissa's question, I'm not sure in which ways you're asking if it's similar to Scratch. But I'll get set up for the next one. So I think pencil code's very easy to set up. You know, at the beginning of the session is sort of where I start with students. I find that the students in middle school are very quick to pick it up. When everyone gets logged in, and I'll start showing them the tutorial and sort of the different menus, they're not listening to me like a minute into it because they're busy dragging stuff out, seeing what it does, looking at each other's screens, saying, how'd you do that? That sort of thing, just immediately. So in my experience, it's been very easy for the students to use and for our teachers to use. All right, so the second guide is for a language activity, which is, it's a program that I copied from the, what's the curriculum called? So Pencil Code is like sponsored by Google, and so they have a bunch of activities for a bunch of different subjects. And so from their computational thinking curriculum, I copied this chatbot, because the actual code of it is too complicated to expect a student to be able to build it from scratch. It's too complicated for me to build from scratch. But once we have it as a base, we can then add on it or use it in interesting ways. So that's what I did with this next one. So I think, yeah, Terry posted the link, the bit.ly link to, there it is again, this activity guide that I have on the right-hand side. So again, you can do an intro to pencil code if students have never seen it before. And then if you click this link, it will copy the code for you. I was in the block-based side previously, so we can turn it back to text-based. You can't, I've never found a way of changing the proportions of this blocks menu to the workspace to the output. So unless you make it bigger, it can be hard to see without scrolling all of the text. So that's one of the bigger limitations I've found with pencil code. But this is the base program that you can work from. So if you, the way I'd recommend doing it is get it, like copy this program. When you click on this, there should be, when you have a save, if you can see the save button, you should be able to save like a different version of it that you can then edit. But the way I do it is I just open this program and I'd run it and, you know, see what happens. So if you say, ask me anything, then I can say hello. and it'll respond, hello, I'm waiting. And usually when you get to this point where you type in something and it starts responding automatically, at least for we worked with early high school students on this. The students that we worked with, I was surprised how much their eyes lit up when we got to this very first step. I was like, oh, you haven't seen anything yet. Don't worry about it. But then the chatbot is designed for Lady Macbeth originally. So you can think of things that you'd want to ask Lady Macbeth, like, what do you think of murder? And she'll respond something Lady Macbethy. So she says, I love power. I will do anything for power. So once you do like a little bit of just playing with the program, then we can go into the prediction phase of, if I say this thing, what should she respond? And so at this point, it's helpful to actually look through the program. And you don't have to, understand exactly what all the setup says, but you can get to when hello or hi, you'll return this. So if I said hello or hi, it should return hello, I'm waiting. And you can test this. Ask students to predict. If I said prophecy, you can ask them to predict what it would say. And so if you said prophecy, this would come back. And so that prediction process takes, maybe 5 minutes or so. And then you can start getting into sort of the edge cases, I'd call them. So what happens if you misspell words? What happens if there's 2 keywords in a single sentence? What happens if it's capitalized, or if it's supposed to be capitalized, but it's not capitalized? That sort of thing. And all of those you can I like for the students to just imagine what they think makes sense and then test it out and then work in pairs to explain why their prediction wasn't correct. And so just for the sake of time, I won't go through, all of the answers to those questions, but in the activity guide, there's multiple questions. So what if you misspell words, capitalize words, add punctuation, use multiple keywords, or there's no keywords in the text that you write? What happens then? And so the answer to that is, if there's nothing that it recognizes, it will return one of these phrases randomly. Then after they get sort of familiar with that predicting step, they can start modifying it. So one of the things they can do is they can go into the return and change what Lady Macbeth would say in response to one of these keywords. That's easy to do in this case. Anything where there's a white field is easy to change. However, if you want to add words on, so like if you wanted to add to hello and hi, if you wanted to add hey, there's no easy way to add that in the block space side. So this is another good opportunity to introduce the text-based side and start getting them a little bit familiar with text-based languages. And just like in the previous waves example, for this, we're just modifying the program. We're not adding, anything substantially new. So we want to use what's already there as a template to add whatever it is that we want to add. So say we're going to add hey to this list of words. We can see that after hello, there's a comma, and then there's hi. We can look at the next group, power, comma, kill, comma, Duncan, comma. So if we want to add hey, then we can add a comma after hi and hey, and then there's no comma at the end of each of these, so we shouldn't add a comma at the end. And we can go back to the block space side, it'll recognize it. The important thing that I found when we were working with students is that just because you change the code doesn't mean that it's automatically implemented in the output. You have to run the code again for the change to take place. So, well, I should have done it without, if I hadn't hit rerun again and I typed in hey, it would turn back one of those random responses. But because I hit run, now if I say hey, it'll say hello, I'm waiting. So we went from the predict of if I say this thing, what should the program return, to being able to add and modify a little bit. And then the next step is that so we added like light modify. Now we can heavily modify the program. So if we keep the base of the program the same, but just change what the keywords are and what the responses are, then we can change this into pretty much any sort of chatbot. So an activity that we have our students do is they'll change the character that it's for. So instead of being for Lady Macbeth, they'll change it to a different literary character. Something else that we've had the students do is we've asked them to make it not a chatbot with a character, but sort of like a dictionary that you can ask things to. So we'll have different literary devices, and we'll say if the person using the chatbot asks what's allegory, it'll give a definition of allegory and an example from whatever they're reading. So this can be sort of a cool new tool for annotating books in that way, instead of, at least how I used to do it when I was in grade school was, you highlight and you mark this is alliteration and sort of this is what it does. You can instead have them create this chatbot that when the user asks what is alliteration, it'll give a definition and an example from the book that they're reading. So that's just a couple of examples of ways that you could heavily modify this, building upon this base to reinforce the learning objectives in language arts classes. And students find it really engaging, from my experience at least. And they really like, the teachers really like that they can see the process that students are going through. If they're stuck in a spot, they can see, based on what exactly they're doing, why they're stuck, or if it's like a concept or if it's just a bug sort of thing. They really like that it helps identify those misconceptions and concepts because they can see the process that students are going through better than sometimes like a discussion will allow them to. Let's see. Yeah, I think that's the end. Obviously, you could, this is also probably a 90-ish minute activity, depending on how in-depth you want it to be. It could turn into a full project if you're using it as sort of like an annotation tool. But that is the chatbot. Any questions at this point before the last one? Yeah, exactly, Grant. We haven't made it yet, but one thing that we wanted to do for language classes is to make something following a similar structure to this, maybe not exactly, to have students define how you would conjugate verbs. So it would require different pieces. We haven't exactly figured it out, but if you could, the idea is that if you could teach a computer how to conjugate verbs, then you have to really know how to conjugate verbs. And that's how we frame all of these activities with our pre-service teachers. Is we start with, do you agree that teaching someone is a great way to learn something? And everyone says, of course. And so we say, okay, this is an opportunity to teach a computer about this concept that you're learning about. The computer is endlessly patient. It's, never going to get tired. You can try as many things as you want. It doesn't matter how wrong they are to begin with. And so that's how we sort of frame all of these activities with our teachers, is this is an opportunity to practice teaching something, to learn, and to really demonstrate that you know the concept that you're learning. So yeah, we're working on a conjugation tool, whatever, or app, I'm not sure what it'll end up being, for language classes. All right, the last one is drawing with geometry, which is the most open-ended one that we have here. And the thing I like about the open-ended nature of this is that you could use it in a computing class, or you could use it in a math class and sort of dial up or down the computing concepts or the math concepts. So I'm not trying to learn geometry when I was sort of playing around with these different tools. So I would just sort of guesstimate a number. It'll make more sense when I show you, but I would sort of guesstimate. But you could have students actually calculating out these different geometry pieces as a way of practicing geometry or math principles. So in the activity guide that Terry linked, I'm again going to click on this link. And you can either start with this pre-populated code, or you can start from a blank space, or you can select, half of these things and just delete them right off the bat. But what I'm going to do is I'm just going to run it, and there are 3 shapes that we've drawn. I'll make it full screen. So the first one's just a sort of basic iteration. All of these are building upon iterations to make patterns that, because of the pixelation of the screen, end up looking sort of cool in some way. So the first one's just it's this little for loop at the top. So for 24 times, it's going to move forward 100 pixels and then turn right 75 degrees. And so you could have students calculate out, if it's turning right at 75 degrees, how many times is it going to take to complete the entire 360 degree area. Of course, it's not as simple as just adding up to 360 because of the angles and everything. But that's sort of a simple one. And then the next one is this purple one, where we draw a square, but then at the end have it turn just a little bit to the right so that it's drawing squares and squares. So it gets this sort of complex well, obviously it's 2-dimensional, but it adds an additional dimension to the image. And because it's so finely, because the angles are so fine and everything, because of the pixelation, it ends up being something sort of cool looking, despite it just being squares drawn over and over again. And then the last one is a snowflake that, so I taught a PD in November, and winter break was coming up. And so one of the teachers wanted to do this with their students, but they wanted to use it to make snowflakes. So, it's a good way to do that. It's using iteration, it's using, different angles and everything. And so we started with just these pieces, the move forward and turn right, move forward and turn right, and using a for loop as the other ones do. And then what we ended up adding was actually a pretty complex concept, which is adding a function with parameters so that you could draw the different pieces in multiple sizes. So what we ended up doing was we made this function that we just called a flake, and a parameter, which is the size. So this parameter acts as a variable. And we made it move forward, the size, and then all the angles were pre-prescribed. And then we can call a for loop that calls the function of flake in a small size and then in a large size. And that's how we get this snowflake with the different sizes. So all of that is to say that, I really like this activity because you can tell students, try things, be creative, try making something really cool. You can share with your partner, you can share with a lot of your other classmates and see what they're doing. The thing I love most about being in classrooms is when students, they get up to see what other people are doing, and then they invariably ask, how did you do that? And then, each of the students, through purely just figuring it out through trial and error, gets to sort of be the expert and say, well, I did this and this is how it works and that sort of thing. So I love giving those students those opportunities to really feel like they own something, that they're doing something that their classmates find interesting, and then for the classmates to learn from each other rather than me saying, do this and draw that and, pick this angle. I like this one because it allows them to just be really creative and see, if you make that a triangle instead of a square, what does it look like? If you make it a rhombus, what does it look like? So having them create multiple shapes that all sort of work together. And then you can also use those coordinate plane things, the coordinate planes to move the shapes around. So you can add multiple like we have here. And it sort of reinforces a lot of different math concepts.
There's a question from Ari.
So the question is, can you have the code start a particular line so you can mod or debug? I don't actually know of how to do that. Say if I were just working on the snowflake, and I didn't care about drawing the rest of it, I would just select all of these and move them up to the top as much as I can. Put it below the speed so that it's at least there, and then it'll draw the snowflake first. And well, it causes all sorts of unintended consequences, but then you can stop it, and that way you don't have to run through the whole program. It's weird that it won't scroll a little bit. Oh, that's a cool idea, Grant. All right, well, we only have about 8 minutes left. So if y'all have any questions, like we've said, these activity plans that I've been using to sort of guide the the activities I've been showing you are available online wherever you want. Pencil Code's free. You can create an account. There's I don't get any spam or anything from them. So it's easy to use, I think, and not it's worthwhile to use. It doesn't come with a bunch of extra stuff that you don't want. We continue, as I continue to work with our faculty education faculty, we're continuing to make more activities like this to integrate computing. So we'll keep producing these. I'm also working with our CS endorsement students who are, so they're existing teachers, but they're adding computer science onto their certificate. So one of the things we have them do in the classes is create an integration activity for their class. So we had, this year, we had an economics teacher create a graphing, a way to graph the supply and demand of something, which was really cool. So I'd have to ask them if we can share those sorts of things, but there's also lots of these sorts of activities in, I'll have to look. It's Google's computational thinking curriculum. So exploring computational thinking is where I got some ideas or just some of these activities. Yeah, I don't know who created, I thought it was Google that created Pencil Code initially, but they sort of.
There was a Googler that created it. I just sent him a link to see the team.
Yeah, I really like it because you can switch back and forth between block space and text space. I know that's sort of something people are really thinking about now, is if we start teaching with block space, there's tons of reasons to start teaching in a block-based environment, especially for elementary and middle schoolers. But then sort of thinking forward to how do we get them to then translate that to text-based. So I like not necessarily coding from scratch in the text-based side for this age group, but just switching it so that they can see what that looks like in a text-based side and modifying here and there just to get a little comfortable with it so that in high school they're prepared to do those sorts of activities. I should share, so I'm adding my email address to the chat in case anyone wants to contact me about any ideas that they have or need support for anything. So that's my email address. I'm at Georgia State in Atlanta, and our goal as a school of education is that every one of our pre-service teachers has experience with at least one of these integration activities, so that when we're in downtown Atlanta, so a lot of the pre-service teachers that we serve are from underrepresented groups in computing, and they teach in Atlanta, which has a lot of students that are from low SES families, from families of color, especially families who are Black or African American. So, we're trying to give them tools to get their students interested in computing and, make it so it's something that they experience without thinking for whatever reason that it's not for them before they have to make choices in high school about whether to take a computing class or not. All right, well, I'll stick around in case anyone has any additional questions. Other than that, enjoy your break before the next session.
Thank you, Dr. Margulieux. Is there anything you need from me? Awesome. Great session.
Thanks. Y'all are very kind. I should say, if people are sticking around, one of the things that we prioritize in our work is making sure that we use tools like pencil code or other web-based tools so that you don't have to buy, because like a lot of our teachers are going to school districts that don't have the resources to buy robots or even Arduinos or Raspberry Pis or that sort of thing. So we are focusing on web-based activities that, as long as they have a Chromebook or something with an internet connection, they can use it. That being said, we have found that pencil code doesn't work great on mobile devices like cell phones. So if that's a consideration for you, we haven't figured out a solution yet. I wish I had something to tell you, but that's something that we're currently working on.
Yeah, unfortunately, some of our students only have mobile devices. They don't have the benefit of a computer, laptop, and or physical computing devices. So something we need to work on. Your day, Dr. Margulieux.
Thanks. I'll talk to you soon.
Yes, ma'am. Take care. Bye.